Hi everyone and welcome to this video on graphs of exponential functions. I know, could it get any more exciting than this? Probably. My name is Darren from Maths Guru. Thank you very much for finding this content. Hopefully you find it useful. What is the video all about? Well, the learning objectives are always going to be behind me. Understand what it means to be growing exponentially, and that is quite important. Understand what a graph of an exponential function looks like. Understand the important parts of an exponential function and know how to apply transformations. Now this starts to build. And as I say in my recap, hopefully by now you've realized that methods is all about looking at what a function looks like or a graph looks like and then basically moving it around. You might be asked to find turning points. You might be asked to find crossing points and roots and all that type of stuff. But fundamentally, methods is learn all of the important graphs, know how to move them around, and ultimately find crossing points. Yes, because from that you can work out all sorts of information. Right, and ultimately apply it to application questions. So we looked at the square root, the hyperbola, the truncus, the cubic, quartics, and I'm sure there are many, many other graphs. But there is one more graph that features quite heavily in this course, and there we go. It is the graph of an exponential. And there is a great example of an exponential function, all right? So basically it's a curve, all right? And if you put money in a bank and leave it without touching it and not putting any money in, then it will grow exponentially because interest compounds exponentially. If you're doing general maths, you will be a gun at that by now because of your financial maths component. If not, I'm really sorry, but the general mathematicians have way more math literacy in terms of finance than perhaps methods kids do. Right, now, firstly, I'm going to break it down and look into the idea of the graph of the form y equals a to the power of x. Now, a, for the moment, we're going to deal with the number greater than 1. All right, so because, well, firstly, if we did y is equal 1 to the power of anything, it's basically just going to be a straight line. Why? Because y equals 1 to the power of anything is just a straight line. If you don't believe me, fire up Desmos or your calculator and have a look. So a nice easy one to start with is the graph of y equals 2 to the power of x. And putting it into Desmos, this is what it looks like. Yes, it seems to curve up and get higher and higher and higher. And if I was to go out to infinity and beyond, it would theoretically keep getting steeper. But the important points to note here are this: where the graph crosses the x-axis. So for the start, the graph in this situation crosses at 0, 1. Interesting. It has a point at 1, 2. Okay. Could we have predicted both of those points? Well, again, if you are aware that this line here is my y-axis, otherwise known as x equals 0, if I had the graph of y equals 2 to the power of x, where x equals 0, then 2 to the power of 0 is, oh, hold on, 1. So in that situation, it would seem fairly interesting that this is going to cross 0, 1. So my next question is, what about the graph of 3 to the power of x, or 4 to the power of x, or 5 to the power of x, or 100 to the power of x? Do we know where that is automatically going to cross? What about that point 1, 2? Well, again, if I had y is equal to 2 to the power of x, and we're letting x equals 1, well, 2 to the power of 1 is 2. So again, it seems that we could maybe start to predict 2 of the points on this line. Now, what is this all about? It seems to bottom out here. Does it ever cross the x-axis? Well, actually, what we're going to find out is no, it never actually crosses the x-axis. It gets closer and closer and closer, but never actually crosses it. Aha! Well, we know there's a term for that, and that's an asymptote. What is the domain of the function? Are there any x values that this couldn't take? Can I have negative values of x? Can I have, for example, y equals 2 to the power of negative 3? Well, if you've watched any of my previous videos, you will know that Mrs. Hurst, the love of my life, said that that negative sign is basically 1 on 2 to the power of 3. So yes, actually, we can have negative values. And so we find out that the domain is all real numbers, from minus infinity to positive infinity. What about the range of the function? Well, having just spoken about it now, if we know that this here is an asymptote, well, it suggests that no values will ever be lower than the x-axis, and so my range in this situation would be real plus, not 0 to infinity, because 0 is not included, so r plus, for example. And these things become important for you to remember and to learn, because Once you can sketch a base function, life is good, all right? Once you can work out what the base function of a graph looks like, we can later on translate, dilate, reflect, and it shouldn't be too much of a challenge, all right? So let's look at the graph of y equals 10 to the power of x, right? Well, what do we now see? Well, if I look at my points, my crossing points, what do you reckon that crossing point there is? Well, again, it's actually 0, 1. Why is it 0, 1? Because if we had y equals 10 to the power of 0, what is that? 1. So when x equals 0, y equals 1. Does it cross through any other point? Well, yes, because we now know that if we had y equals 10 to the power of 1, that gives me 10, which gives me this point here. So again, for a base graph of 2 to the power of x, 3 to the power of x, 4 to the power of x, I have two specific points I can plot straight away. And if in an exam you were asked to sketch, the examiner would be looking for evidence of those 2 points there. We know the shape now. The shape starts off, sort of close to the x-axis, goes through those 2 points, and sort of goes to infinity on beyond. And again, could we predict this? Where's the asymptote? What's the domain of the function, the range of the function? Well, the domain again is all real values. The range is going to be real plus, because effectively we can't go on the x-axis or below x-axis, and it's got this shape again. All right, awesome. Believe it or not, you've now pretty much learned everything about the important features for the graphs of the form y equals a to the x. All right, let's just go through them one by one. The x-axis is an asymptote, tick. These are for base graphs. The y-axis will intercept at 1, 0, and the point 1a, what do I mean by a? Or whatever that is there, whatever the base number is, that will sit on the line. We'll be able to describe this graph as exponential in terms of growth. Now, for those of you who've done general maths on the financial component, obviously you know that there is sort of a trick there in terms of what exponential is, but for methods we don't really cover that. The domain is real, the range is real plus, and as x tends to negative infinity, y gets closer and closer to 0. Okay, so that's just another way of sort of explaining this. Now, dilations and more dilations, it's really, really interesting. This is a bit of a side note. If we look at the graph of y equals 2 to the power of x, and we look at the graph of y equals 10 to the power of x, believe it or not, this graph here, to get to here, is nothing more than a dilation from the y-axis. And you're going to turn and say, huh? I'm going to try and talk that one through. It's a little bit sort of not higher order, but it starts to link all of the maths together. I can write y equals 10 to the power of x as 2 to some sort of power of k to the power of x, right? So I don't know what k is at this moment in time, but there must be some sort of value of k. There must be a value of k that when I do 2 to the power of it, it gives me 10. That sort of makes sense. And using my index rules that we've got from previous chapters, that gives me 2 to the power of kx. Now again, for those of you who are sort of linking together your transformation stuff, that there basically is a dilation from my y-axis of factor k. How do we know that? Well, we know that the only way we can get that is 2 to the power of x on 1 on k. All right, so I said it was a dilation of factor of k from the y-axis. That's not true. It's a dilation of factor 1 on k from the y-axis. But ultimately, again, if your fractions knowledge is good, you know that 1 on k, so if I did that as keep, change, flip to go back, that's the same as x divided by 1 on k. Keep the first one, change that, and then reciprocate, and so they are effectively the same thing. So to go from this graph here to this graph here, basically we have a dilation of factor 1 on k, that k value giving me whatever I need to get to 10 from the y-axis. All right, so pretty cool to know. Is it going to be useful later on? Who knows? Right, graphs of the form of y equals a to the x, where a falls between 0 and 1. All right, so in this situation, some sort of fractional value. So if we now look at the idea of what the graph of y equals a half to the power of x is, well, first things first, let's say, well, it seems to be actually reflected, right? In this situation, it's still going through 0, 1, but now it's going through minus 1, 2. Why is it going through 1? Because previously, if I'd had the graph of y equals 2 to the power of x, that basically crossed through at 1, 2. This is crossing through at minus 1, 2. Why? Well, again, if we sort of shortcut this a little bit here, we know that the half can be written as 2 to the minus 1. 2 to the power of minus 1, and that's all to the power of negative x. Yes, so a half is 2 to the power of minus 1, raise that to the power of x, gives me 2 to the power of negative x. And again, if you're really good at your transformations by now, then that minus sign there simply means that it's the graph of 2 to the power of x, but reflected in, that's right, the y-axis, all right? Because that x has become minus x, it's a bit counterintuitive. And again, knowing that sort of information tells me that if I was going to sketch this graph here, firstly, I'd probably want to write it in that form. Then I'd be turning around as a quick pencil sketch in my margin, sort of saying, well, that's my important points there. That's my 1, 2. That's my 0, 1. My reflection here means that basically all of my y values, all of my x values are just basically going to become negative, and in which case that would be minus 1, 2, still stays as 0, 1. And there we go. Nice, easy way. And because it's a sketch, I don't have to be overly accurate with all the rest of the points, so long as those two are identified. Right, what about this? Important information relating to the graphs of that, where a falls between 0 and 1, not inclusive, because again, 0 to the power of anything doesn't make any sense. All right, the x-axis is an asymptote, so the x-axis still stays as an asymptote. As x tends to infinity, y tends to 0. Okay, the y-axis intercept is 0, 1, so it still stays, that y-axis intercept still stays as 0, 1. The domain of the function is real, the range of the function is real plus. And that sort of makes sense because all we've done is really just reflected it in our y-axis. Okay. Now, using a CAS, plot the graph of y equals 2 to the power of x on a CAS calculator and hence find correct to 3 decimal places the value of y when x equals 2.1. Let's see if we can actually do this on my CAS calculator. So bringing up my CAS calculator, I'm going to clear off what I was working on before. I open up a graphs, and again, I'm using the TI Inspire. Sorry, ClassPad guys. Again, the functionality is fairly similar on your calculator. So if I now go 2 to the power of x, he says, once again, hitting the wrong button. So if I now go 2 to the power of x and hit enter, ka-ching, move my graph down a little bit, and then let's sort of make that a little bit wider. Now, what does it want? Find the value of y when x equals 2.1. Well, the great thing here is I can go menu, trace, graph trace, and that point there sort of can move up and down, left, right, and center if I want to with my cursor. All I'm doing is use my cursor. But actually, if I type in 2.1, literally just put 2.1 on my calculator and hit enter, out comes the value of 4.29. If you're not sure where that is, it's down here. And again, if I had a different value of x, say 1, I could put 1 in and it will give me 1, 2. Oh, hold on a moment. We expected that, didn't we? Because, so what happens if I make an x value of 0? He says, hitting my microphone, 0, 1. Yes, the theory is being borne out. Very excited by that. All right, so that's one way to do it. What about the value of x when y equals 9? Not so easy to do in terms of just being able to put a y value in, but I'm going to hit tab, and I'm going to put a line of y equals 9 in. That's simply all I've done there. So that line now is basically y equals 9. How am I going to find my x value then? Menu, analyze graph, intersection, and I'm going to do it to the left, and I'm going to do it to the right. And if I pull that down, there we go. So we now know my y value is 9, my intersection is 3.17. So that's graphically a way of being able to do it. Is there another way of doing it? Well, I can go calculator, and I could use my solve function. All right, so I've got y equals 2 to the power of x, y equals 2 to the power of x. So y equals 2 to the power of x. Actually, I don't need to use solve. Why am I even doing that? I just do 2 to the power of 2.1. Whoops, 2.1. Hit enter. And because my calculator is in exact mode, once again, out comes 4.28. And because it wanted to 3 decimal places, I'd obviously be in that situation writing 4.287 as my correct answer. The value of x when y equals 9, then I would need to use my solve. I'd say 9 equals 2 to the power of x. He says, come on, comma x, hit enter. And because my calculator is in Exact values, it came up with all that stuff there. And as such, again, to 3 decimal places, what would that be? 3.170. All right, so using my CAS, nice and easy. So let's turn that off for a moment and squidge over there. And again, for those of you who are downloading the notes, there are sort of calculator screenshots here giving you an indication of what the answer should have been. Actually, I'm going to go back and bring up my calculator one more time because I've just realized if I go back to my there, what do you notice? Well, it's not really helpful in the terms of, let's just go back and do menu trace, graph trace, and let's put in, what did we want? 2.1, hit enter. Now, what do I notice here? I've got 2.1 comma, 4.29. That's not in 3 decimal places. If I go menu, settings, float, and I do float 4, for example, and do an OK, there we go. So float 4 will give me 3 decimal places, 4.28. So you can also change that in terms of your graph. Hopefully that is useful. All right. What have we got here? Yep, that's just looking at the information. And again, this screen is just sort of showing you, well, hold on, we can actually work out what we do here with the calculator. Right, transformations of exponential graphs. And obviously, this whole course is about transformations. We've looked extensively at transformations in previous sections and have looked at the idea of y equals x to the power of a half, a half to the power of x is the same as 2 to the minus x. Let's see how we can transform these graphs. Sketch the graphs of each of the following pairs of functions. For the second function in each pair, okay, he says, for the second function in each pair, state the equation of the asymptote, the y-axis intercept, and the range. The x-axis intercepts need not be given. All right, so again, you could find them using calculator methods, but we're not going to. Right, so for the first part A, we're going to look at the graph of 2 to the x. So again, what I tend to do is I do a quick pencil sketch of what 2 to the power of x looks like. So that one there is going to be 0, 1. That one there is going to be 1, 2. Job done. My asymptote is at the moment on the x-axis. Right, what is 2 to the power of x plus 3 going to look like? Well, I seemingly have my same base function, but I have literally just translated it up by 3 places. So in that situation, I would now be drawing my final graph with my asymptote because that will move. All right, so there we would have y equals 3. I would draw my graph like that, and also make sure the examiner is aware I understand what happens to each of those points. My point 0, 1 will now become 0, 4. Because I have translated that thing up 3 points, all of my y coordinates will have 4 added to it. And again, my point 1, 2 will become the point 1, 6. Now, so long as I have put that properly on my diagram or in my sketch, then, theoretically speaking, the examiner should be happy. I'm going to add arrows onto the end of each of these simply because my domain wasn't restricted. How do I know that? Because there it said my domain is all real values. And so because I can't draw a graph with all real values, I'm just going to put those arrows on as well. All right, ka-ching. Did I get it right? Oh, I did get it right. I did. I thought I pulled it cat. All right, now obviously in this situation here, I haven't got my asymptote shown on my graph. I probably should have put that in at y equals 3, but pretty much that's the graph I'm going to end up with. Right, what's the next one? Ooh, 2 times 3 to the power of x plus 1. Now again, a lot of people get quite tricked with the idea of 2 times 3 to the power of x. I don't know why people then think that becomes 6 to the power of x. It really isn't, right? You've got to get used to the idea of this being dilations, reflections, and translations in terms of, so we got the graph of 3 to the power of x. So if I was going to be doing this sort of in an exam, there we go, there's my base function. Again, 0, 1. This one crosses through 1, 3. Now, what does this tell me to do? Well, dilations first. That 2x, or 2 times, means I'm now going to dilate factor 2 away from the x-axis. All of my y values are going to double. So I now know, again, I tend to just cross these through. That would now become 0, 2. And that would become 1, 6. Yes? This is a sketch. I can do anything I like on the side of my paper just to make sure that it all works out. What happens next? So dilations done, reflections none, translations plus 1. So again, this now gets moved up by 1. All right, so what we're now going to do is we are going to add 1 on to each of my y values. So that now becomes 0, 3, and that becomes 1, 7. All right, where would my asymptote be? Well, my asymptote would now be at y equals 1. This is just a visual reminder such that when I sketch this, we'll hopefully get the right answer. So let's see, did my graph go through 0, 3? Well, there we go, it's going through 0, 3. Will it cross through 1, 7? Yes, that is my point 1, 7 there. Oh, I'm cooking. Yeah, and obviously in my graph or on my actual sketch, I'd be doing that as y equals 1. Whoa, what's next? Whoa! Right, so again, we've got the base graph. We've been given our base graph of 3 to the power of x. So a quick pencil sketch of what my graph of 3 to the power of x would look like. There we go. That again is 0, 1, 1, 3. And again, practice makes perfect. The more of these graphs you do, the more you're putting it into your muscle memory. And your brain is a muscle, believe it or not. Oh, I don't know. That's a PE teacher's going to tell me off now. What have we got? So, dilations. So, are there any dilations? Nope, there don't appear to be any dilations. Are there any reflections? Yes, there is. So, that there tells me the first thing is that that is going to be reflected in my x-axis. Right, so that's a reflection in the x-axis. So now let's draw a quick sketch. So it's going to get to here. So that now is going to be 0, -1, right? Because when you're reflecting in the x-axis, your y values become negative. And that point there is now going to become 1, -3. So that's that, dilations, reflections, and then translation. So then we're going to move this up by 2 units, which means that I'm going to add 2 onto my coordinates. So 0, 1. Sorry, I'm going to add 2 onto my y coordinate. And that there is going to become 1, -1. Where would my asymptote be? Well, it would go from 0 to 2. So my asymptote should be at y equals 2. There we go. So there's my asymptote of y equals 2. And what have we got now? Well, is it crossing at 0, 1? It is, because I think we're looking at my green graph here. And does it go through 1, -1? It absolutely does. And again, in that situation, yeah, a lot of boys, and it is mainly boys, sorry lads, turn around and go, oh, I'm not going to do that, I'm just going to do it in my head. Sadly, you will lose a load of marks. There is no two ways about it. There are things that examiners are looking for, and breaking it down did not take very long. All right, doing that as a diagram did really not take that long. All right, sketch a graph of each of the following. All right, so again, I know that I'm probably over-laboring this, but it is really, really important for later. Y equals 2 times 3x. 6 to the power of x? Nope. So what I'm going to draw now is I'm going to draw a quick pencil sketch of 2 times 3. So I know what 3 to the power of x looks like. That will go through 0, 1. And that will go through 1, 3. I'll have some arrows on here. I'll have y there, and I'll have an x there, because we've got to be accurate, or, you know, we've got to at least make it look like we're drawing a sketch. And we'd use a pencil and a ruler. 2 times, oh, that's okay, because this is a dilation from the x-axis. Yep, it will basically double all of my y values. So in which case, that now becomes 0, 2, and that becomes 1, 6. Right, so there's my pencil sketch done. What am I going to do now? Probably draw it properly. So there's a straight line, and there's a straight line, and there is x, and there is y, my asymptote. And a lot of people say, how do you draw an asymptote on the x-axis? Very carefully. So it's y equals 0 is my asymptote, and then I'm going to sketch my graph that does something like that. And I'm going to make sure that I tell the examiner, hey, I know what I'm doing, 0, 2, and that's going to be 1, 6. And again, does it look like it's stretching off? Nope. But for a sketch, that is perfectly acceptable. And probably I would just put my arrows on either side there because my domain isn't limited. Hey, cool. Right, what about this one? Sketch the graph of the following. Y equals 3 to the power of 2x. Oh, y equals 3 to the power of 2x. Well, again, I now know from my transformations what that 2 actually means, because that is the same as y is equal to 3 to the power of x on a half. And we know that when we are doing this, it is going to be a dilation from the y-axis, because it's affecting the x, from the y-axis a factor of half. All of my x values are going to be halved, right? And I'll explain more about that in just a moment. So let's start off with my quick sketch of my base function. Well, my base function is 3 to the power of x. We've already dealt with 3 to the power of x. So again, that's 0, 1, and that's 1, 3. Okay, so what are we doing now? We are dilating it a factor of half. Everything is going to squeeze in by a half. My y values aren't going to change. It's my x values that's going to change. So all of my x values I'm going to multiply by a half. 0 times a half stays at 0. So the good news is that point stays there. 1 times a half means that that basically is going to be a half in. So it's going to be a half, 3. And lo and behold, I'm pretty sure I have all of the information I need. So if I was going to draw this now, I'd be drawing my straight lines in pencil. There's my x. There's my y. Let's draw my asymptote in really badly. Y equals 0. And what am I now going to do? So we said it went through 0, 1. So there's 0, 1. And we went through at the point a half, 3. And there we go. So we're going to sort of do this. And let's do arrow on the end there and arrow on the end there. And basically, again, if you noticed, all my sketches look pretty the same. What the examiner is going to be looking for, though, is evidence that you know that those points there are existing. And if they give you a grid, please draw it accurately, all right? Grids are there to help, but unfortunately end up tricking people because they think, well, I'll just draw a random sketch. Please don't. Right, what about this one here? Y equals -3 to the -2x plus 4. All right, well, you think that's tricky. I see through your tricks. Quick pencil sketch. Now, obviously, this one here is going to be interesting because it's got dilation. No, actually, it's got two reflections, dilation and a transformation or translation. Oh, so much. Right, so remembering we have to do it in the order DRT. So dilations. Are there any dilations? Yes, there are. So first things first, we've got that 2x there. Ignore the fact it's -2. It's 2x. It basically means that I'm going to dilate factor of a half from the y-axis, right? So again, the points are going to in by a half. So if this is my graph here, that point there is 0, 1. Let's say that point there is 1, 3. So we now know that this point here is going to stay where it is because if I'm dilating, I'm multiplying all my x values by a half. 0 times a half stays where it is. And that point there now becomes a half, 3. All right, so there is my dilation done. Reflections. Do I have any reflections? Well, we have two reflections. We have a reflection in the y-axis and a reflection in the x-axis. So if I reflect this in the y-axis, that means my graph is going to end up coming something like that, where this point now becomes reflection in the y-axis. So that becomes -0.5, 3. All right. So, but that point still stays as 0, 1. And then I'm going to reflect that in the x-axis, which means that my graph is now going to do something like that, which means that this point here becomes -0.5, -3. And that point there becomes 0, -1. Again, notice how I'm building it up. I can use different colors. I can use pencil. In fact, you'd be advised to use pencil. And then what's going to happen? We would then translate that up by 4. So my final graph is going to look something like this because my asymptote is now going to be at y equals 4. Sorry about the dreadful color. Let's try something else. It's going to do something like this. And I'm going to put some arrows on the end there because my domain. Now, if it's going to be through +4, right? So again, all of my coordinates I now need are going to effectively cross through at 4 higher. So that's going to be 0, 3. So I now know that that point there, and the examiners will be looking for this, 0, 3. What will this point here become? -0.5, 1. So -0.5, 1. So I'm going to do that there as -0.5, 1. Ka-ching. Now, again, the question doesn't ask you to do the x-axis intercepts. There are ways of you being able to do that on your calculator, but theoretically speaking, this is almost the end of the video. If you can subscribe to my YouTube channel, please do. Spread the word to anyone out there that you know if this resource has been useful. Hopefully it has. Have we, and do we understand what it means to be growing exponentially? Tick. Understand what the graph of an exponential function looks like? Yes. both for values of a greater than 1 and between 0 and 1. Understand the important parts of an exponential function. Yes, the domain, the range, where the asymptotes are, and those two important coordinates. And know how to apply transformations to exponential functions. That's the last 20 minutes of this video, he says jokingly. I think that's the end. If you can subscribe to my YouTube channel, I've already said that. That would be great. Leave a comment below if you think the video was any good. Hopefully, I'll see you in another video. But for now, take care and bye-bye.